So, and we derive this from KL divergence, right? So we wrote the KL divergence, and so if we look into the integral form of the KL divergence, so we derived a lot of properties for KL divergence. That's fine, and then we said that. So basically, we started with measures, right? Probability measures, and then we said that KL divergence is convex function, and then we computed KL divergence. We said that KL PQ is not equal to KL QP, and hence it's not a norm. Okay, so KL is not a metric. So these are the things we derived, because for a metric we need a symmetry, and yeah, so and then we saw we tried to generalize KL divergence. So while doing so, we brought in something called F divergence. Generalized KL divergence. Okay, so when we generalize KL divergence, so initially, the KL divergence was given to us as P given Q, and if we use the integral form, then it's Px log Px by Qx dx. So this is a way to measure two probability distributions P and Q. Okay, so this was our starting point, and what we have said is that we also proved this in the last class, is that if I minimize this KL divergence, then this is equivalent to doing maximum likelihood estimate. Okay, so we proved this in the last class. So what it told us is that one of our goal in generative modeling is like estimating the density from given data. So if I have given data, I can fit a distribution, and that's what maximum likelihood means. But then we saw this connection that if I minimize KL divergence, then it's equivalent to maximum likelihood estimation. But maximum likelihood estimation as such does not give much interesting thing here. But what we saw from the KL divergence is, given that it's in the integral form, we can derive some variational approach. Okay. So as I said, variational approach is a very generic idea used in a lot of areas, also in solving like PDE. So often this is intractable to integrate this in its form. So you would like to create a variational approach for this, and to do that we went for a couple of steps. So first we had a generic measure, it's called F divergence. Okay, so then we defined something called F divergence between P and Q, and it's a slightly reverse form of this, but it becomes a special case of this. So it was Qx F of Px by Qx. So this was our second step, where we said that this is our KL divergence, then why not generalize this using some function f. Okay, and it was found that f must be it helps if f is convex, then it gives you a measure which is interesting. Okay, so there is a paper I cited on that where they do the detailed study of F divergence, and this F, not just it has to be convex, but F of 1 must be 0, because that would signify that this is a good measure, in the sense that when Px equals to Qx, then I expect that this measure is 0. So in that sense, F can be any convex, but F of 1 vanishes. Okay, and this is an expectation that P equals to Q, it should give me 0. So this was the generalization from the statistics point of view, because in statistics people try to compare two distributions. Then the next step of idea came after noticing that this is a convex function, and we introduced conjugate. Okay, and conjugate function allowed us to create a variational form of that. So the conjugate way, and we also use the fact that it's I mean, we can use the reflexive property like F double star is F and so on. So that we did as a next step, where we were looking for a variational form where F star T with Tx minus Fx. And this is something we have seen in convex analysis as well, where we create a conjugate. So this is called conjugate, and it is convex because it's a supremum of set of affine functions. So it's convex in T. And then later we noticed also that for a convex functions which is also closed, let's say, meaning the epigraph is a closed set, then we also saw that F star star becomes F. Then we went to the measure and we said that, okay, let us do that. Since I want to replace F by some variational approach, here the variation is created by the T here. Okay, so what we so noticing that F double star is F, we did one more star here, and so basically we replaced F by F star. So this becomes so we do double star here, right? So this becomes star, and then double star is F, so this becomes this. Okay, so so we can put this this function in terms of conjugate here. That's what we did. So then in the integral we had this supremum thing, okay, and that was the last step. Okay, so when we did that, then we have we can so the way our F divergence changes is df pq is qx, and then we have this supremum. Okay, so supremum over T. Actually, when we change this to Fx, then we will swap x and T. Okay, so we want to change to x, then this becomes T, and this becomes T. Okay, so Fx will be replaced by this supremum of T, Tx. So in place of x, we have Fx by Qx, right? So that's what we did. So this is T Px by Qx and minus F star T, right? So this is what we did as a third step. First step was scale divergence. Second step was generalization to F divergence. Third step was creating a variational approach via introducing these conjugates. Supremum inside, we saw in the last class that it's not really, we want to keep supremum outside, okay, so that we know exactly what, because right now supremum being inside means that it's a pointwise supremum going on here. For each x, we find a t, and so on. So this is not very convenient. So we wanted to put this supremum out, but then if we have to put this supremum out, then t has a nonlinear behavior, because for every x, t could be anything, because t will be the one which supremizes this. So this is a difficulty. This is the math difficulty or real analysis difficulty. So we want to bring this supremum outside, but then we cannot now just keep a t inside. So I cannot just say that take a supremum out and this is just t px by qx. This is wrong. F star t. This is clearly wrong, because I am treating t as a linear function right now, but while it was inside, it was being supremized. So essentially t could have taken any values like that, which is nonlinear. But if I take supremum outside, then I am saying that treat t as a linear and this whole thing overall as a function of x and integrate, which is wrong. So that's where we need a little bit of help from operators and approximations. So okay, this is still revision going on. So so what we said is that okay, we cannot keep t linear inside, because that will be clearly wrong, because behavior of t because of the supremum would be that of a nonlinear. I mean, it may be a t itself, but in the most generic case, it may be nonlinear as well. So what we said is that why not change this t to some operator, okay? Operator that emulates the behavior of t, which is like a pointwise changes. So then we said that okay, and this is for every x that t is found. So that should be t of x, because for every x, I want a output from t of x as some t. Okay, so that's what we did also in the last class. So we did this. Okay, so then we said that okay, so we're taking supremum out can be done, but t cannot be left as a linear, because supremum being out means inside the integral it is seen as a linear, and I will integrate is treating as a linear. Supremum will be taken later on, right? So that will be false. So hence now we were looking for a t that will create this behavior. Okay, so now this, with different choices of this, we of course there will be many choices for t. Okay, we will look for the one which matches the best, right? So there will be many operator. You have variations of t that you have that are likely candidate, but obviously we want the one that matches this t that was pointwise inside. Okay, so hence we keep this as a variation here. Okay, this is one of the reasons why we call this while going from here to here, we call it variation. The variation comes from this trick, okay, where now I am looking for a generic operator t. Okay, and with different choices of t, now there will be like an optimal t for which this will be achieved, but then in practice you may choose some t which is specific, but that will give you a lesser value, because this was supposed to be the supremum. So if I specify t with something which is not necessarily optimal, then I will end up as something like this, qx, and let us say I specify this with some t1. Okay, since I may not know what was the optimal t, so I have to have something which will be acting as a lower bound for the t1, right? So this is like px qx minus f star t1x. So this introduction of t has created a variation for me which will make things tractable. Okay. So today our goal is to have a practical idea out of all this. So, so where we left last time is, I will write those precisely now. So what we have as a final variation step was this. So supremum of t, so set of all operators. Okay. So I'm not very precise here. I'm continuing from there. So basically, yeah, this is just a rough sketch for me. Okay. I'm just explaining here, but what I really want to specify is that you supremize over all possible operators that you may have. So some operators will be bad, some will be good, but out of all this, there will be one which will give you the optimal. Okay. So once again, as I said in the last class, I have not proved this this analysis result, but maybe if I have time, I will. So this is more about operator theory, approximation via operators, and so on. Okay. A simpler result would be when you take limits of sequences, and you can take those limit outside of the integral. Okay. So these are the things. If you are a math student, then usually you study these things. And when is it that I can take the limit out? Okay. This is a specific case. Okay. Interchange of limit and integral. Okay. What are the properties of f? You can do that. So under certain properties, you can prove that limit this and is equal to limit outside. But this is more tricky than that. This is like not even sequence. Okay. I may not have a sequence here because this is like so many t is possible here. Okay. So certainly proof is there. We are using that, but not doing it here. So it would be good to do it as a project. I will upload a reference where you will do this proof and present it as a project. Okay. So where we left is tx px minus f star tx qx dx. Okay, so this is exactly what we have. Basically, we took the qx and multiplied the qx, and hence qx got cancelled. So in the simplified form, we have that. Tx is the variations that we were looking for, different choices of t we can play around with, and different choices of f. Okay. So KL divergence is one of the measures, and the f divergence tells you that you can play around with many convex functions with this property to be satisfied, and then you may come up with variety of ways to approximate dfpq. Okay, so now let us go into the specifics, right? So if we break this, then this is expectation of tx, and this is expectation of f star tx with density qx, and this is expectation tx with the density px. So we can also write this as an expectation, right? And overall, this is a, so t, if I can parameterize by, because t, as I said, is our choice, right? This is now a template for us, and which t I choose, that's our choice. So let us say t is some t phi that I want to choose, where phi is the parameterization of t. Changes in phi gives me different t. Okay. So using parameterize family of functions t phi to approximate the optimal t, to approximate the optimal function t, can minimize an F divergence between P and P theta. So P is our P could be our underlying distribution, and P theta is the distribution that we kind of approximate the P. Okay, and so with this setup, we would like to write the GAN objective or the min-max problem. So this is arg min theta and then supremum over phi. So T phi is our T phi is the parameterization. So phi is the parameterization, and we have a supremum there, and E T phi x minus. So here x follows P, and Q for us is P theta. Okay, so this is expectation of x follows P theta, F star T phi x. So T phi is coming from, as before, it was a supremum over T, and then we want to minimize this E T phi and the basically the difference, and that's the for which theta this this measure is going to be 0. Okay, so that's why we have a min over theta. Okay, so and as a further step, so this we write this as arg min theta and supremum over phi of expectation of x follows P T phi x minus expectation of F star and then T phi G theta Z. Where Z is G theta, I mean Z goes to G theta Z via the mapping. Okay, so what we are saying is that X is produced via some generator G theta that acts on Z. Z is, let us say, some known distribution from where we can sample, and then it creates the X. So G acts like a generator. Okay. T phi that you see, it acts like a classifier. Okay, so I will write down in next few steps what I mean. Yeah, this is a proof from real analysis. Yes, I'm not going to do the proof, but in the space of, because you are allowed this T to be all possible T that you have. So in that case, yeah, I don't think continuity is a requirement here. You are allowed any T that goes from X to R. If I have not missed anything, there is no restriction on T. All possible operators T are allowed. Yeah, I don't see any restriction on T. That should be the case, I believe, because if I am doing this point to a supremum, it can create very bad kind of functions without, sometimes not even smoothness may be there. So hence I think we should allow T to be any operator. Okay. So we can do this proof as a project, I would say. Okay. So where we are now, so 15. Yeah, so if I have to relate it exactly to what was proposed by Ian Goodfellow in the GAN main paper, which is called Generative Adversarial Net. So that's where a specific form of GAN was proposed. Then I will write in that form. So what was done in the Goodfellow 2014 paper. So in 2014 paper, Ian Goodfellow et al. And the paper name is Generative Adversarial Nets. All right, so in that they had a clever idea of setting t phi, okay, and what I said just few seconds ago is that I will see t phi as a classifier and g as a generator, and it will be transformed into a min-max problem. So someone is generating, and then there is a discriminator. They'll say, okay, your generated items are good or not. Okay, so that's how things are going in that direction. But if there is a specific, so if you remember, let us say a classification problem, then you have like losses, right? BCE losses, cross entropy losses, and what do you see there, right? Log of y 1 minus log of y. Okay, so if you want to see t phi as a classifier, then maybe choose t phi as log of something that you see as a level. Okay, and then from there t will be seen as I said, it's as a classifier basically. So let us substitute t by log x, okay, or log of kind of like the discriminator, okay, the classifier. I mean, the output level produced by the it should be log of y, so level produced by the discriminator. Okay, so okay, so so parameterizing so t phi so is equal to log of d phi of x. Okay, we want to use notation d to denote it's a discriminator. Okay, so as I said, this is your template now. You have to play around with that. These guys played around with this. So t phi, choose t phi to be log of d phi, where d phi itself will be some parameterized neural network. Okay, so neural network is just a function, okay, with some parameters that you can tweak, just like polynomials with the coefficients are the parameters. Here neural network can be seen like that, okay, some parameterized family. So choose this, then if we substitute it there, then what do we get, right? So this is the Goodfellow. So this is theta f is arg min sup phi, and expectation of x from p, and log of we are just substituting here d phi of x plus e zq, and log of 1 minus d phi g theta z. Okay, so if you have implemented GAN at some stage, then you are at home, you usually see these things, right? So d phi is a neural network parameterized by phi, g theta is a neural network parameterized by theta. You have to, yeah, this is exactly the BCE loss, log, and then log 1 minus. Okay, so there is someone which is classifying the outputs produced by the generator GZ, right? So let us So this is the Goodfellow's. Okay, so what I will do now is I will write down the complete algorithm, okay, to be like sure about what it is there. Now it is worth writing the full algorithm so that you know how to implement. Okay, so let us write down the algorithm. Okay, algorithm for GAN or training GAN, right? So this is our first full-scale algorithm for generative modeling, right? So this algorithm, if you implement in Python, you start generating images, okay? So for number of, so we start a for loop for number of training iterations. Okay, so however many iterations you want, this is also a parameter, okay? Do the following steps. For k steps, now k is a parameter. K steps, do sample mini batch. Okay, I will explain this algorithm, okay, so don't worry. First let us write this. Sample mini batch of m noise samples Z1, Z2, Zm from prior prior distribution PZ. Okay, and this noise samples will be something that we know. Okay, it could be uniform distribution where I know how to sample. Okay, it could be standard normal. So something that I know from where I can sample such some m number of noise samples. Sample mini batch of m examples. So here by examples, it means something that from your training data. So in your training data, it could be let us say set of cat images, right? So these are the example samples, all are the same thing, right? From data generating distribution P data X, and then update the discriminator by ascending its stochastic gradient. So update the discriminator by ascending. So it's like a gradient descent ascent, but since it's a max for the discriminator, because discriminator goes with phi. Okay, so D we have maximize over phi. So hence, if I have to maximize, then I will use gradient ascent. Okay, that's what it's trying to say. So update the discriminator by ascending its stochastic gradient. And its stochastic gradient is given by grad phi d1 by m log of d of xi plus log of 1 minus d g of zi. Okay, I am using this bigger notations d and g. Okay, although I have used smaller notations here, or to be consistent, why not use the same. The good thing about these notations is that it also tells you the parameter we have. Yeah, if I do that, then I have to do it everywhere. So let us do it everywhere because we want to be consistent here. So what we have is a gradient with respect to phi. So let me do it. So these are gradients with respect to phi, and these are this is the expectation term here going on, right? And this is d of d phi xi, and this is g theta, and this is d phi. Okay. So basically I have just copied over this. Since I have m examples, the expectations will be carried over those m examples. That's why we have a sum of I equals 1 to n m. Okay, so this expectation term now becomes that, and this is telling me that you compute the gradient with respect to phi. Okay, and gradient ascent. So let us say this is g. So let us say it's ith loop, right? So gi is this. This gi might conflict with this, right? So let us say this is ui. So I will use this gradient to update the current state of weights, and then so this is the end 4. So there are a little bit of detail. I will come back. Okay. So let me first write the algorithm, and then I will expand on this. So this is the discriminator loop where we ran it for k times. So this we are supposed to run for k times. The discriminator update happens k times. Okay, and generator happens once only. Okay, in the original proposal. Okay. So now let us now go for the generator part. So sample mini batch of m noise samples z1 zm, and in this case since it's a generator, it's a mean problem because theta goes with the g, right? So in this case it's a minimization problem, so we have to do the gradient descent. So then descent, update the generator by descending descending its stochastic gradient, which is, I hope I can like fit this here. Then the algorithm also completes here. So this is theta for the generator, and 1 by m and log of 1 minus d phi g theta zi. Okay, so when you took gradient with respect to theta, the first term vanished because there was nothing to do with theta. So that's why you see only this term being remaining. Okay, because the first term has nothing to do with theta. However, for the phi case, phi is involved in both the terms. So that's why you saw both the terms remaining in while taking the gradient with respect to the phi. But with respect to theta, there is no theta here. You have only left with this. Okay, so you can completely like gradient with respect to this theta, it will be 0, right? Completely. So nothing to do with that. Just take gradient here. And in the original proposal, so this was proposed in 2014, and then many tweaks, things keep happening in GAN. Okay, so this may not be the exact algorithm that you might see if you do some Google search. Okay, so this is the original algorithm. So you will see many variants. Okay, so it's fine. So a lot of research has happened in tweaking GAN. And what they do in their original idea is they do gradient descent, but also with some momentum update. But for our case right now, we may not like think about all those momentum updates and so on. We can think of this as some gradient descent and ascent. But that's better to do it in optimization class. Okay, so let us see this algorithm again. Okay, so the original proposal. So what is happening here is that you are training a generative model. Okay, so what is happening here is that someone gave me set of images, like my favorite are cats, right? So xm, and these are cat images. These are the examples, samples, whatever you can think of. It depends on what you train on. Okay, you can train on cat, you cannot expect the output will be dog. Okay, It may look like some kids look like dog also, so but it may happen, but that will be by chance, right? But it depends on what is your training data. So let us say in this case you fix some training data, okay? It could be a mix of cat or dog also, okay? So it depends. If you see the current day generative modeling, they use all the images from the internet, so hence they can produce many things, okay? But when you are coding as your own, you cannot hope to take all possible. So you will specify certain number of examples. In this case, let us say cat images. Let us say m number of them. Okay. So these go here. Okay. These are your xi's, and this is the data we have p data. And what it says is that you also create some noise samples. These are our Z1, Z2, Zm, and the lines sample mini batch of m noise samples. It's like saying that take m of them, okay? So, okay, going by this, what it means is like your number of examples may be many, and you take some m number of them out of those, okay? So that's what it means. It's not like total you have. It's not like what I said just now. It's like total samples is m. Not like that, because here it's saying sample mini batch of m noise samples. So basically, it's expecting that you have many, and in the first step you will take m. Okay, that's your mini batch. So batch of images, and on that batch of images, this is defined. Okay, the expectation I will take on those m. Next time I will go to the next for loop. So k equals to 1, it will happen, take m, and then for k equals to 2, it will take another m, another set of cat images, and so on. Okay. So sample mini batch of m. So that's why I did it, and then we also generate noise samples. Okay, as I said, noise samples could be, let's say, uniform distributions. So that I can generate. Okay, basically random numbers, random vectors I'm supposed to generate that follows uniform distribution. So that's also done here. And those are the things I need to define these expectations. So yeah, so with this I will. So this is like our loss, right? So we want to train the discriminator. So discriminator is parameterized by phi. Okay, so basically training the discriminator means that updating the parameters of the discriminator. Okay, so in this case I could have, yeah, here it's the intermediate one, right? So the update step could look like this: phi I plus 1, my new set of parameters for the model is, if I do the simple gradient descent, right, minus grad of the ui that I computed, and this was ascent, sorry, so this is plus. And you can use some learning rate eta. Okay, so this is the update, let us say, of the discriminator, update or the ascent of parameters of the discriminator, right? So that's what this UI step is, where I did an ascent, and initially your phi will be random, because you don't know what you are searching the phi anyway, right? So since you want to update phi I plus 1 from the old phi, a natural question is, what is my first phi? What was phi 0? So phi 0 you have to take random, okay, and let the model learn the optimal one, because the iterative method, it will keep improving. Okay, so basically it's about finding a maxima, and this is my phi, okay, and the function I have is d phi, and then I'm asking for which values of phi I can maximize d phi. then obviously I don't know where to start, right? So my phi 0 could be somewhere here, and and I use the gradient method. So gradient method tells me gradient points in the direction increase. So if I take a gradient, then this will certainly tell me that, okay, go this direction, okay, and then I get phi 1, and then I take another gradient, the gradient points in the direction increase, so it will lead me to this, and eventually gradient becomes flat at the maxima, okay. So that's where I will stop. So this, we expect that we reach phi star. In this case, we did gradient ascent, okay. So as I said, obviously I don't know where to start, right, because it's a given function. I don't know much about the function, so that's why this phi 0 can be something random, or if you have some nice guess about your function, you can choose that initial point carefully if you have some idea about the function you are maximizing. But in general, if you don't know, then you have to put something random. So that's how you will update the model's parameters, okay. And these parameters, as I said, like for the moment I have not described, but I will take them as some black box, okay. So I kind of like it's a parameterized model, so I will learn it via X to tune my parameters phi, and once it gets trained, it becomes a good classifier that I'm hoping for. So so this for the moment is a black box in the sense that you can think of any parameterized model, okay. So just like if I have a fitting problem, okay, I keep doing this because this is the simplest you can think of. So parameterized models for me are the polynomials in theta, which are theta, let us say in this case square, theta 1 x square plus theta 2 x plus theta 3, okay. So with different x, I have found theta 1, theta 2, theta 3, which are the best that fits this, okay. Now you can think of these as a very generic parameterized models, which more popularly now it's taken as neural networks, okay. So d phi is some neural network, and for our purpose we don't have to immediately go into neural network right now, but a very basic idea could be given, okay, and if we need, we will do it in detail a bit later. So the neural networks, the way it goes is like it is inspired from the neurons in our brain, and it creates certain neurons, okay, a network of neurons like this, okay. It tries to emulate something like we have. What we have in our brain is more complicated, but it tries to learn from there. So it tries to build a neural network model, but it is nothing but a function approximator, okay. So your input goes in, okay. So let us x1, x2, x3, and so on, and then these inputs are let us say multiplied by these weights, okay. So it's theta 2, theta 3, and so on, okay. So then we have a kind of a linear combination of these. So theta I, xi, okay. So that's when all these xi's are connected to one neuron, let us say this guy. Then this is a linear combination of these x1 with theta 1, x2 with theta 2, x3 with theta 3, and then I sum it. So then I get an output for this neuron, but then I also do some kind of a some activation of these data, okay. Basically I apply some other function here. So it could be some simple functions like sigmoid, okay. Some nonlinear function, let us say, you apply on this, and then you have these outputs. Then again recursively it's connected to this, okay. So this way you keep doing linear combination, activation, and so on. So that becomes your parameterized model, just like polynomials were your parameterized model. But here the parameterization makes it very interesting, more powerful, because there are nonlinear activations, and then these linear combinations are there, and so on. So this makes the model very powerful. It can learn prediction problems to very high accuracy, and so on. Okay, and this is the main reason behind all the interesting things coming out from machine learning these days, which is an area of deep learning. Okay. So basically, if I have many layers, I make this more complicated, then it becomes deep neural network. It's called deep learning. So for the moment, I won't go in detail, but I will teach you this in more detail later on. So for the moment, for the GAN purpose, we think of these as some black box where there is a function approximator and with some parameterization theta I, and these are the parameterization theta I I'm learning here. Okay, with the gradient descent, I'm trying to adjust these parameters, okay, and tune them as much as possible based on the data I have. So so this is what the training for the discriminator is happening here. Discriminator is trying to maximize, okay, its value, okay, and hence we have to do gradient ascent. And now in the next step, so after you have done k steps, then you train the discriminator, so sorry, generator, and you sample now m noise samples, okay. And for the discriminator, you needed both noise samples and the actual samples. For the generator, you need only the noise samples, okay, because generator only needs in theta, right? It's in theta, so it only needs access to gradients of this. So while computing gradient, it only needs the this term here. So you sample m noise samples, and then, and in this case you have to descend because it's a mean over theta. So you will descend by taking the gradient again, and in this case obviously descent will be, in this case for the theta, it will be the theta I plus 1 will be updated at theta I minus eta, okay. And then let us say this is ui and this is vi for the generator gradient, okay. So this is vi. So this is the generator parameter updates. So a natural question is, okay, now this is the algorithm. I understand the algorithm, okay, because it's now pretty clear what I am supposed to do. Okay, by looking at the algorithm, pretty sure what I'm supposed to do. And these things I have to just take it as a black box, in the sense that if I am computing the gradient of these guys, which involve log of some neural network, this will be done by the library itself for you, because these are complicated functions, and computing gradient means, like, there is an idea, something called backprop, but these things are done by the, like, computing these gradients is done by the, let's say, Python code itself. So we don't have to worry about that. These gradient calculations are done by the software, okay, and the Python library. Usually use PyTorch or something, and then similarly this gradient computation will be done for you, okay. So you don't have to worry about computing these gradients by hand, okay. In fact, it's very tricky to do it by hand, not possible. So as such, algorithm is pretty clear, okay. There is nothing there anymore, okay. It's a simple idea. We are solving a min-max problem, and to solve min-max problem, we do gradient update and gradient descent. Now here itself, from optimization point of view, solver point of view, you will have many variants, obviously. What we used is a very simple one, right? I use gradient ascent and descent, and this is called like GDA, right? But these things are done the more interesting variants of the better variants, these things are optimization issues, right? So these things are better handled in optimization course, right? So there are GDA, there is ConOpt, there is extra gradient, mirror descent, CGD, even our method, even our another method is still submitted. Okay, so we have like so many people. There are people who spend all their time just in improving the training of the generative model. Okay, so this itself, you can make a career just in working on these things. Okay, because this matters not just for publishing paper, but also for industry, because industry is looking for quality images. So these algorithms that lead you to better minima and maxima, better solve for this, essentially means that it leads to better minima, or basically in this case it's a saddle point problem. Okay, this is a min max. So there is no minima or max. It's like you are, you know, the horse saddle, right? So you are looking for a good consensus between the max and min guy. This is a two-player game problem, right? In two-player game, there is no absolute max, absolute winner. There is no absolute loser, in general, because that would mean someone winning mean, if it's a zero-sum game, someone winning means someone loses, right? So in game theory, it's more about agreement. Okay. So you have to make a deal that, okay, I'm happy up to here, I'm happy up to here. That's why the total, if you minimize, it will not be like 0 or something. Okay, it will settle to something else. So it's saying that, okay, if I go from this side, this is your generator. Okay, so generator is saying that, okay, I want to minimize this as much as possible. Okay, but then this is saddle, so it's a little bit hard for me to draw. So this way it's decreasing, but actually this way it's increasing. So in the board it's difficult for me to like this. So saddles are like this. Okay, so the generator is saying that, okay, I want to minimize, okay, my values as much as possible. And obviously for the generator, the good values are when it goes right till here, but the discriminator will be unhappy. Discriminator is saying that discriminator goes like this, right? So if you see this as a 2D values, then generator paths, like a good happy path for generator is these paths, and for discriminator it's trying to go like this, and then both are trying to make a deal that generator will say, I want to minimize as much as possible, obviously. Then discriminator say, no, I want to maximize, so I want to like kind of go like this. But the discriminator itself also may not be able to kind of it is better to do it in 1D, okay, because I will complicate things for you. I'm just thinking, let us do in 1D only, because so let us do like this, just 1D. So so one of generator is like this and discriminator is like this. Let us keep it simple. So generator will say, okay, I want to minimize, okay, my theta values I want to minimize, and this says I want to maximize. So this guy is going like this and says, oh, okay, I should go all the way up, okay, and this guy is saying I should go all the way down, but both will settle somewhere here. Okay, so this is your saddle point, right? And obviously, like, there may be more characterization of these points as well. But there is something called Nash equilibrium points. How do you characterize those, and so on? Okay, we can look into those, but The idea here is to settle on something mutually satisfactory rather than absolute winner or absolute loser. Okay. So this whole theory of all these min-max problems, and specifically for GANs, these are the methods. Okay. As such, min-max problems are very, very wide. It's also seen in many other areas. Okay. It has a lot of applications. Obviously, in markets, economy, operation research, it's a lot of things there. But for machine learning point of view, in GAN is a generative model where min-max is used. Okay. There are other models where min-max is not used, but GAN specifically relies on this. So hence, you are led to these various methods. Okay. There are so many things. Okay. SGA symplectic methods are there and so on. So I would better cover them in the optimization course, which I teach separately, and you can watch those. I upload those on YouTube videos. But for our purpose, we see this as some optimization. Okay, so we think that there is some optimal way to do these things, and as I said, if we do it well, often as we gradually move away from this, quality of images are improving here. Okay, so if you search some of these papers, you will see quality produced by these, and this, no matter how well you train with this, is just not good optimizer. Okay, so quality of images never become better after a point. So this is like another line of research people work on. Okay, so from practical point of view, it seems to be fine. You may implement these methods even with a simple choice of D or G. But even if you use neural networks, you don't have to do anything anyway. These gradients are computed by the softwares anyway. So you can do these implementations. Now I will prove few things about the optimality. As I said, like this is a min-max problem. Okay, if I'm doing only mean, then I won't be happy, because in mean problem, getting stuck in a saddle point is considered bad. But in min-max problem, we are looking for saddle point, in fact. Okay, so we want to see where does these guys settle. Okay, if it is a min-max problem, then for GAN, what are those optimal points? So there are like two small results to be proved for this, because knowing those optimal is good in the sense that when you're training, you know that, okay, if it's settling down to certain value, then you know that your code is working well. Okay, so this small theorem I will try to prove for GAN. So we have seen a practical implementation, but then we also want to know when the code runs, where are the losses supposed to settle. So those are provided by this theorem. And okay, so proposition 1 is for G fixed, optimal discriminator D is given by D star. So we denote the optimal by D star. Gx is P data by P data x plus Pgx. So what this result says is that your optimal discriminator should be like this. The P data by P data plus Pg. Pg is the generative distribution, and P data is the real distribution. Okay. Okay. So let us define a quantity which will be a shorthand for us. So as I said, GAN is a two-player game. So recall, it's a two-player game. So this is the proof that starts from now. It's a two-player game. So which is min over G and max over D. So sometimes I switch over capital G or small g. Okay, I hope this doesn't make, yeah, because I take this from papers and then I prefer to keep their notation so that I don't mix things. So log of, right, so log of d of x plus expectation of z follows p z z, log of 1 minus d of g of z. So this is the min max, exactly what we did, but I have changed small g to capital G and small d to capital D just to keep the notations from the paper itself. But everything is same, right? So for a given G, right, if I'm looking for the optimal discriminator, then for a given G, I want to maximize, right? So basically it's a maximization just on D, okay? So from above, from this equation, from above, so for a given G, discriminator D wants to maximize VGD. All right. So if we expand VGD in terms of the integral, then this is P data log of dx plus basically we have PG of x log of 1 minus dx. So we have this, okay, we have written the expectation in this form. We expect that both are defined over the same x, okay, so the integral is over all of is over the x. Both PG and P data are on the all defined on all x, okay, so that's why we do that. And now we have to maximize this, right, because we have to so there is a result that says that AB in R square, the function y a log y plus b log 1 minus y achieves maximum in 0, 1 at a by a plus b. So we see the integrand as a log y plus b log 1 minus y. Okay, so dx in our case is y. So we can prove this by it's again optimization, right? So we want to maximize this a log y plus b log 1 minus y and see what is the optimal value it takes, or the maximum value it takes, right? So we take a differentiate and equate to 0, right? And let's see what happens. So this should be pretty simple. So dy, so let us say this is what fy function, let us say. So this is f prime y, we take derivative and equate to 0, right? So a by y plus b by 1 minus y minus 1, and this should be 0. So this is a by y is b by 1 minus y. So this gives me a minus ay is by. So this implies y is a by a plus b. And this is maxima because double derivative, I believe, is positive. double derivative must be positive, right? F double prime or negative maybe, right? So F double prime A y, right? So minus A by y squared, and there is already a minus here, right? So this becomes a plus B by 1 minus y squared. There will be minus also now. So there is one more minus here. And this seems to be less than or equal to 0. This whole thing minus, which is less than or equal to 0. This implies y, this is maxima. Okay, because double derivative is negative. So indeed we verified that this function is achieving maxima a by a plus b. So in our case a was A was p data, and b was pg, right? So it's evident from here. Okay, I will just write one statement. Okay, so this is maximized when the what the problem at hand is for which values for which conditions on, for what value of y, in this case y is dx, right? So here y is dx, and for y equals to p data by p data x by p data x plus pg x, where I set a to be p data and b to be pgx. Okay. So what we are asking here is, what is the value of d for which you this integral becomes max? And we said that okay, this is of this form, and y is our dx, and then it's like for which value of y it's max, then we solve that it must be of this form. Okay, so d star, our optimal for this VGD is max. So this was the proposition 1 that we proved just now, and so if I put this now, I know now that an optimal discriminator is of this form, p data by this. I can put this in the VGD now. Okay, so I put the optimal VGD there, and then so like there is just small one more theorem, and that's it. So with this optimal D, the min max game becomes, or mini max game becomes CG. So let us say I have like maximized over D, so D goes away. Okay, so this is max over D of VGD, and we have maximized this for E x p data log of D star GX plus E z pz log of 1 minus D star G gz. So it is maximized for D equals to D star, and that's what we are going to substitute now. So this is expectation of x follows p data, and log of p data x by p data x plus pgx plus expectation of x pg and log of pgx. We are supposed to use this, that's why we are writing this, p data x plus pgx. We want to find now the, so we want to see what optimum value now CG will settle on, given that I am provided CG, given that I have provided an optimal discriminator. Our goal is to see what would be CG eventually. Okay, so let us now say that CG will settle on minus log 4. Okay, that's the result. So it's not like everything is going to 0 or something. Okay, so CG will settle on something like minus log 4. That's the optimal value it can take in this min max problem. So this is the theorem. Global minima of virtual training criteria VG is achieved if and only if PG is P data. At that point, CG achieves the value minus log 4. Obviously, for the generator, if you see, if our goal is to train a generator, right, that starts generating realistic images, right? So one thing I may not have shown you is, one thing that I may not have told you is, like, after training GAN, how do I generate, right? So that was the part when we have this theta z, right? This is our generator, right? So when we wrote those algorithm to train GAN, then we had this d phi, gz, and so on, right? And they are like running this min max problem and so on. But once the training stops, what you have in hand as a generator is this g theta, for which theta you have learned, and z is a known sample. Z, you know, like z is some uniform or something known where I can sample, and you pass that z to this g theta, which is usually a neural network, and it will start producing new images for you. So after training, you throw away discriminator, and generation process is just with gz. So this result is telling me that an optimal scenario training of the GAN will be when the probability distribution of the generator matches the actual distribution, right? That's what we expect in that I'm training GAN in such a way that it becomes the original distribution. Okay, so this is what we are trying to prove. So we know that the optimal discriminator that we have proved just now is P data x by P data x plus PGX, and this is if and only if, right? So we can have it like both way. So if let us see the one way, if PG is P data, then what happens, right? So if PG is P data, so meaning generator just learn the true distribution, then in that case I can put it here. Okay, then what would be the optimal discriminator value, right? So optimal discriminator value will be P data x by, since PG is P data, I can put PG P data here, right? And then P data gets cancelled and we get a half, right? So P data x plus P data x, which is half. So what this tells me is that if I am training the GAN, then if I am checking the value of the discriminator, and if it so happens that the discriminator scores come out to be half, then I know that my training is good. And if you see this in terms of the probability, then the another interpretation is that now the discriminator is like completely confused. And making discriminator confused is a good thing, because when you are creating bad images, then discriminator is sure that it's bad. Okay, and when you are creating very good images, absolutely good realistic images, then also obviously it will say like, but the point of generative modeling is to create something new, where the generator gets completely confused. It's not able to tell you completely that it's bad image. It's also not able to tell you that it's a good image, and that is considered an optimal in GAN, because that's when you are saying that even the expert is not able to distinguish. That means that it must be doing something interesting, image is coming out, right? That's what it means. So that's why discriminator optimal value comes out to be half. Once this is what the theorem is saying. Once your generator starts producing a distribution which is the true distribution, discriminator is confused. Okay. So that's the optimal discriminator score that we expect. So if I am running a training algorithm and if I am printing these values, and if I get a half, you should be okay. Okay. If you are getting 0, it should not be okay. If you are getting 1 also, it shouldn't be okay. But it's converging to half, it's you can say, okay, my training is going well. Okay. So okay. So this is like and if this is the case, right? If PG, so this is this forward implication we are trying to do. This is if and only if. So what we are doing is the if part. So if this happens, then we are supposed to show that the CG value also, okay, which is the next step we are trying to prove, is minus log 4. Okay. So with this, hence CG is expectation of x p data log of d star gx plus pz dg gz. So since I know that in this case when pg equals to p data, and so CG is, I just written the definition of CG for the moment. What I am going to do next is replace dg star by half. So there is a half here and 1 minus half here. So combined we should see minus log 4 overall. Okay. So this becomes log of half plus log of half, and this is equals minus log 4. Okay, minus log 2 is minus log 4. So we have done this forward implication. If PG is P data, then we conclude that the CG value is minus log 4. Now we want to say that the other way around. Okay, but like we have to say that this is the this minus log 4 is only if PG is P data. Okay. So let us do the other part. Okay, this is the only step I need. Okay, then we can stop. Okay, for the GAN, yeah, this should be enough. Then there is something called WGAN that we will do in the next class. There also very deep theory is going on there in WGAN. Then we will go to diffusion models. Okay, WGAN will take 2 classes. Okay. So now we do the other way. Now we say that minus log 4 is the best we can do. Okay. So CG equals to minus log 4 is the best possible value of CG, and reached, and this is achieved only for, so this is why we say it's only if part, right? Only if PG is P data. Only if PG becomes P data. Now let us look into CG now. So because, we have to prove that this is the max it can. So let us first write down CG, which was expectation of X for P data and log of P data X by P data X plus PGX plus expectation of X PG log of PGX by P data X plus PGX. So this is, we have written, so this is our CG, right? When we have maximized over the D, then the D takes P data by P data plus PG. That's what we have done. Now, what should we do to make it? We have to prove that it is maximum log minus log 4. Okay, that's what we are supposed to prove. Its maximum is minus log 4. What we can do as a trick is to go to a, so what we will do as a trick is we will transform this into certain divergence, which is like JS divergence, and that JS divergence becomes 0 when PG equals to P data, and what is remaining is minus log 4. Okay, so that's how we will go with the proof. So we will somehow transform this into JS divergence. So to do that, in the Jensen-Shannon divergence, JS divergence, so I will write down that first so that you can preempt what that divergence might be. Okay, I'm JS, and in this notation we have P data and PG. Okay, so P data and PG, and this is actually defined via KL. Okay, so this is KL divergence of P data and PM plus KL divergence of PG PM, where PM is a mixture of P data plus PG by 2. So in this notation we have this JS divergence written for us. So what we are trying to do as a next step is to go there. Okay, so KL divergence you may have seen, right? It's expectation of log of, if you just look at the KL divergence, then KL of PQ is expectation of log of P by Q, right? But there is in the denominator you have not Q, but in place of Q you have P plus something, right? Now looking at here, it is indeed in this form, right? Because Jensen-Shannon says that it's P data by, so this PM is what we are looking for basically. I mean this PM is already in that form, right? So I see this as KL of this exactly, it seems to be, right? So this is the first term is like KL P data and P data plus PG, and then similarly the other one which is with PG. Yeah, so one thing that is more is this half term, right? What we can do is that multiply and divide by half, right? 2, 2, and 2, 2. And what we will do is that this 2 that we need in the denominator, right? For the KL, right? I take this as a 2 here, and this 2 that I had here, I take this is 2 here. Then now it is in the form, but then only thing is like this log half and log half is there, but that's exactly where you had the log 4 also, right? So log half plus log half minus log 4, I took it out. Then what is remaining is now in the good form. So is expectation of, or I can write this directly since I have already explained to you. So this minus log 4 and this half if you take away, this is exactly KL of P data and P data plus PG plus KL of PG and P data plus PG. Now this becomes JS, okay? That's how I define it there, right? So this is minus log 4 plus Jensen-Senner divergence of P data PG. So by doing this, now we have to say that the maximum so minus log 4 is the best possible value of CG. So Jensen-Senner divergence as such is a greater than equal to 0. This guy is greater than equal to 0, and it is equal to 0 only if P data is PG. Okay. So from there we know that the least possible value that CG can get is minus log 4, because otherwise JS is greater than equal to 0. So the best possible value for CG is like the, so otherwise it, so CG we minimize, right? So the best possible lowest possible value for CG is minus log 4, and that happens when JS becomes 0, and JS becomes 0 when PG is bigger. This is exactly what we have to prove. Okay. So that concludes the proof of this. So this was the major result of GAN. So with this we can stop, and then we will study WGAN. WGAN we will spend 2 classes. WGAN is more in practice now. Okay. So it's better that we study the trending thing, and then we go to diffusion model after 2 classes. Diffusion model we will spend 4 or 5 classes. Okay, thank you.